In the general case, the proof is much more complicated, as I told you. But here we are lucky, and this will be very short. Maybe I'll look a bit to avoid I'm in a hurry. So what was this? So X was covered by lines, and I knew that the second variety of the variety of lines was filling up Tn minus 1, the small space of tangent directions where the variety of lines lies. Okay? And the conclusion was that X is conic-connected. That's the content of that. Very, very interesting, because from a kind of infinitesimal information, right, you get some global conclusion. So you know that at the general point, something good happens, namely the second variety is a whole space. And then you get some global conclusion, namely two general points can be joined by a conic contained in X. This is quite, that's something, huh? Try to prove it. You'll see that. That is, okay. And now, here comes the proof. So now, I will look, so proof. Consider the family of lines. So this, as usual, comes with a universal diagram, right? Some Hilbert scheme or Chow scheme or whatever. So here you have the lines, how I denoted them by C. Here you have the universal family. Here you have the projection to X, right? So this is phi, this is pi, as usual. So here, this is an irreducible component of these lines, parametrizing these lines. Here the fiber over a point is a line itself. And this is a tautological map in which the line is embedded in X, right? So as usual, when you have Hilbert or Chow scheme, you have this universal diagram, right? I won't insist because you always work with this. And here you can restrict this when you fix a point. This is what I denoted by Lx. Maybe I put, let me put L, excuse me, for this L, okay, just to be consistent with the previous notation. So, and here you'll have the same thing, but you only take lines that pass through the point X. Okay, good. Now, I will need some more notation, namely C index X will be the locus of lines through X, right? So the set of points in X lying on lines through X. So what is this? This is a cone with vertex X, of course. So this is cone with vertex X. Good. What is the dimension? So I had some notation for the dimension of this family. It was small a. I keep the notation from the preceding lecture. So what is the dimension of Cx? A plus 1, of course. So far we did nothing. Now we began to be intelligent. Namely, I introduce some bigger subvariety of X, which will be the set of points, let's say, Y. Y, or maybe, yes, Y. I have to be careful with the notation. The set of points Y in X such that the two cones intersect. So this is a very nice set and very subtle to estimate. Look, let me make a picture. So this is a cone. This is Cx, right? This is perfectly easy. Now I want to go one step more. I have my family of lines, and I look at all lines meeting this cone. So here at each point, right, there is a growing cone, right? and this is for each point. So you get some horrible set that you cannot very well see geometrically, right? And the point is to estimate somehow the dimension of this set. And this is in general terribly subtle and difficult. Horrible. Please try, even if they are lines. I mean, when you look at these cones, you don't see how they intersect at all. That's really a mess. And you'll see kind of a ballet trying to avoid this, difficulty. Okay? Good. So this set, the set of points from which you can reach the cone by a line, passing through the point and meeting this cone. This is Vx, right? Right? Okay? Good. So maybe I will make some civilized picture. This is x, this is Cx. And now I will take here a general point. Well, this set may not be irreducible. So I take some irreducible component and I take some general point. Otherwise I don't know what means general, right? So this I call x prime. So if you want, my picture will be like this. This is a cone through x prime, this is x prime, and they meet at some point. Okay? Maybe I will call this the point they meet y. Okay? So y will be in the intersection. Okay? Well, so far I did nothing. So far I did nothing. Yeah.
But your y is different.
Yeah, that here y is. Don't piss me, huh? Put z here if you really want, but that you can use any letter, right? I should have used some Korean character to satisfy you. Okay? Now I will make an estimation, and this will be the following. So the dimension of Vx will be the following. So please stay with me. Dimension of this is terrible. Pi minus 1 pi phi minus 1 Cx. How many parentheses I don't know. Minus dimension Cx intersecting Cx prime. Terrible, terrible. And I claim this is 2a plus 2. So I have to explain this. And here is the explanation. So first, you have Cx that you control. This is in x. Right? You take, so you are here. And look, you have to do this. Pack, pack, pack. Okay? Then you will get here some total space. And here you will take the dimension, which this image will be exactly Vx. And that estimation is the dimension of the image is dimension of the total space minus dimension of the general fiber. Okay? So that's the idea. Now let's see first that the total space is of dimension 2 times a plus 2. This is clear because first you are here, right? You have dimension a plus 1, the cone. Now I estimate by the same trick what is the dimension of the pullback. I have to add the dimension of the fiber. But what is the fiber over a point? Lines through that point. So you add a. You understand? So if you do this part, it is a plus 2a plus 1. Right? Okay. Now I'm here. And now I have to do pack, pack, right? But the fibers of this map are lines. So this operation increases the dimension plus 1. So it was 2a plus 1, 2a plus 2. Okay? So it's not complicated. You just have to be patient and look and keep in mind what you want to do. Okay? Okay. So far, so good. Point. Now, I want to write this vice versa. So I do this. So, dimension. It is nice. This is my proof, and I'm afraid to show it to Juan. He will kill me because he trivialized his theorem. So this is, well, it's a special case. So this is 2a plus 2 minus dimension of this guy. Okay? Okay. Oh, maybe one more word. Why is this dimension the correct dimension? Because this was dimension of the total space minus dimension of the fiber, but this is not exactly the fiber. What is the fiber? The fiber is you are with a point Z in Vx, and what is the fiber? Well, if you think, so you have a point here, let us call this Z, right? So what's the fiber? The fiber consists of all lines that pass through this and meet this. But this is the same as counting the intersection points of this line with, right? And these are finitely many. So the dimension of the intersection of the two cones is equal to the dimension of this set. You understand? They are not equal as sets, but the correspondence is finite to 1 because such a line can meet this cone only in finitely many points. Okay? So that's why this dimension, the dimension of the fiber is exactly this. Okay? Good. Now I have this. And now let's be clever. We do the following. Here you want to estimate the dimension of the intersection of two varieties. This is always smaller or equal than the dimension of the tangent space at the intersection. But the tangent space is contained in each tangent space of the two pieces you intersect. So this is always smaller or equal than the dimension of the intersection of tangent space. Where are you? Tangent space at the point. Where do they meet? At y, right? At y of the cone of x and tangent x at y cone of x prime. Okay? Okay? So far, standard. Now comes the really clever thing. So, look. I will change this picture. So look. Right? And now I'm changing it. Be careful. That is to say, instead of looking at the point y as being the intersection of the two cones with vertex x and x prime respectively, I look at the point y as being the vertex of the cone such that these lines are general members of this cone. Because all points are general. This gives me some tremendous information. Because now, look, here, I look at this space. Tangent space to y, cone through x. But a moment's reflection will show you that it is, you can, exchange the 2 points. So speaking about the tangent space at x at this cone is the same as the tangent space at y at this cone. Because along this line, the tangent space is the same. It's in a cone. You understand? So we can switch the two. Okay, similarly for this. Okay, so now I got this. Okay, okay, so now I'm here, right? So I want to intersect these two tangent spaces, right? These tangent spaces are, how do you call this in English? So they are like the train on a rail. They can be put here, you understand? Like if I put oil here and I do this, they sleep, yeah, you can sleep them till here, right? Wait, but now, these, what are these? These are tangent space. So what was this guy? This is my Lx, right? And this is a cone. So here you have the tangent space. Here you have the tangent space, right? Right? And Terracini tells you that these two tangent spaces together gives a tangent space at the second variety. But the second variety was the whole space. This was the hypothesis. Right? So the whole space means here it is the whole Pn minus 1. Right? This tells you exactly that this intersection is of dimension, what dimension? 2a plus 2 minus n. The numbers are shifted by 1 because you passed from this thing to the whole tangent space, right? So you add 1 all over. So once again, how do you compute? So you have the dimension of this space is a plus 1, right? So you add, and then you subtract, right? The whole thing, and what remains, right? And what remains is the dimension of the intersection. The formula for here, and here it is n, not n minus 1 because you are in dimension 1 more, right? So that's the formula. Okay. Okay? Let's look at what we got. We started here. So, maybe I write here. 2a plus 2 minus dimension of Vx, right? We started here. And we had smaller equal this guy. Right? What is written? Right? But Vx is a subset of x. So this is an equality. Right? It cannot be bigger than x. Vx was a subset of x, right? Right? Oops. What is the meaning of dimension of Vx equal n? Let's see. This is my cone through x, right? And Vx was defined, the set of points such that the line, you can find the line through the point touching the cone. So if I take here x prime general, the two cones meet. Now look at this. So any x prime in x general exists, they generate conic pair of lines joining them and contained in x. You see, it's a pair of lines. Okay? And now you have to apply some general philosophy, which is very well described, for instance, in the Bar's book that I have recommended some time ago, that if you have two general points and such two meeting lines, you can smoothen this situation. That is to say, you can deform the pair of lines such that, with keeping the 2 points fixed, such that to get a smooth conic. So, deformation theory, X is conic-connected. This is the proof. So you can, so first you get a pair of lines which meet, and then you can smoothen it by keeping the 2 points. This is a non-trivial result, but the details are very well explained in the Bar's book. You asked me in Catania this. So, okay. So here we proved that it is conic-connected. Now, there was a last mystery in my proof that was related to something called lemma 3, right? Lemma 3, when I said, well, from this we can conclude that Lx is contained in C independent quadrics. That was a missing point, right? Let me simply tell you how you continue to arrive at this point. So it continues like this. So if X is conic-connected, then by a remark that I already made, delta is positive, right? Because the conic passing through two general points enters automatically in the entry locus, right? And then lemma 3 applies. This condition was in the assumptions of lemma 3. Okay? And the conclusion was, lemma 3 was not stated, so relax, it will be in a moment. And the conclusion was that Lx inside P n minus 1 is contained in C, codimension of X, independent quadrics, hyperquadrics. And then I explained how the conclusion follows. Practically, at this point, I explained everything except the potential lemma 3 that was not even stated, and the fact that delta positive was necessary to apply it. But this part now is finished. In the remaining time, I will say a few words about second fundamental form and lemma 3, because it's unavoidable. You have to eat this soup too. It's chicken soup, very hot. So you have to eat it. Okay, so now I explained this part because there are some ingredients, basic ingredients. So I explained these tricks with the contact locus, the entry locus, and blah, blah, and blah, blah. But also, there is some infinitesimal study exactly like in differential geometry, because essentially this second fundamental form is the algebraic counterpart of the second fundamental form of Gauss in projective geometry. But I will present it in a very geometric manner, in which you don't look at some tensors, oh, I hate this, sum of alpha, e, g, k, million times covariant and 2 million times contravariant, and you compute and you compute and you compute and you don't understand, but finally it works. I will give a variant which is geometrical, okay, and very easy to understand. I mean, the definition will be easy. Then I will state the lemma 3, but I won't prove it. But I will give all the information just to understand what's going on, okay? So please stay with me. Okay. I think that 5 lectures would have been better. He will kill me. but I'm sincere because I feel that I need one more lecture. But anyway. Okay. So now something about projective second fundamental form. This is very, very useful, very useful. This will be, let me start by telling what this is in general. This will be a linear system of quadrics on P n minus 1 equals P tangent space, let's put dual. So this is an infinitesimal object which is defined at each general point and is a linear system of quadrics on the space of tangent directions at the point. Okay? And also, to see already how useful it will be, Kanjin already knows this very well, its base locus is made, well, scheme theoretically because it's a base locus, but forgive the imprecision, is made by tangent directions which have contact at least 3 with x at x. Who is the best in differential geometry in this class? Do you remember how these are called in differential geometry? They are called asymptotic directions. Maybe you, I don't know, if your course in differential geometry. Thank God Huang is not around because he will kill you all. So these are called asymptotic directions. I'm not an expert in differential geometry, so don't ask me questions. Okay, so first I described the kind of heuristically what's going on. Now I will give a precise definition. Be careful, this is a non-complete linear system. So in general, non-complete. Almost, in all cases, it is almost never complete. But there is something bad about the notation in standard literature. It is denoted with 2 bars. And in algebraic geometry, when you put something in 2 bars, you mean the complete linear system. And this may be confusing. So please remember, it is a wrong notation. I won't use it. I won't put the bars. Okay? Okay, now I give the formal definition that hopefully I prepared the way, so definition. So maybe one last remark here, just to see how this interferes with our business. So this is made, so the base locus is made of lines, tangent lines at x, which touch x more than doubly. Being tangent means doubly. Huh? There are more tangent at x than a simple tangent. Okay? In particular, lines which are completely contained in x and pass through x have infinite contact order, right? So they are inside. So the point is that this will be denoted, well, like this. Second fundamental form of x at x. And usually there are 2 bars, but I don't put the bars to avoid confusion with a complete linear system. So with this notation, remark, just to finish the presentation, this is always in the base locus of this guy. I repeat, because a line completely contained has infinite contact order, right? So it is automatically inside. In general, this inclusion is strict, of course. Good. Now the formal definition. The formal definition, where is the formal definition? It should be somewhere. I want to keep the good notation because otherwise it's a mess. So, first I will speak about tangential projection. So, you are used to project from one point. Now, please be more imaginative and project from the general tangent space. So, the center of the projection will now be n-dimensional. So, this is usually denoted by x, so x always general point. So pi x will be a map. So this will be projection from the tangent space. So where does it go? So it goes to Pn minus n minus 1, right? So this is Pc minus 1 in our notation. This is a rational map, of course. It is not defined, so not defined where? Of course, in the intersection between x and its tangent space, right? At these points. Okay? So it's a rational map. Very well. Now, this is very difficult to understand. It's terrible. So we have to do something to make it more civilized. And the thing you use is to blow up the point x. So here, excuse me, please. So this will be sigma. Sigma is blowing up x. Okay? And here you have the exceptional locus, which is a Pn minus 1. Right? Okay? And you can take this map and restrict it here. Okay? It is easy to see that this exceptional locus is not completely contained in the set where this map is not defined. So you see, here you have some bad points where it is not defined. So by blowing up, this kind of improves. This is kind of a partial resolution of indeterminacy, right? But you only blow up one point, right? Now, think about this map. What is it made of? What is a linear system defining this tangential projection? Simple. By definition, it is a linear system of hyperplanes containing the tangent space. Or, which is the same, this is a linear system of hyperplane sections singular at x. Right? Now you blow up. And I will tell you now what is a linear system I am interested in. And this is the following. So you take sigma star of the hyperplane section minus 2 times exceptional locus. This is a linear system here. Right? So, why is this natural? Because what is this made of? So, minus 2 times exceptional locus means proper transforms of singular hyperplane sections, right? Right? they all pass through the point, so I can take them all. But I want to take only those which are singular, so minus 2 times. And this linear system has to be restricted to E as a linear system, and it is not complete. But this will be a subsystem where in OE of, and now be careful, sigma star comes from downstairs. So you can avoid the point X, right? H is a hyperplane, so you can take a hyperplane. So this will, when you restrict to E, it will be 0. E restricted to E is minus 1, because this is the exceptional divisors. Minus 1, minus 2, this is O of 2. Right? So, my friends, this is a linear system of quadrics on the exceptional divisor. And the exceptional divisor of the blowing up is a space of directions in X. Right? So, this is the second fundamental form. This is my definition, my object. Okay? Sorry? This thing. So it is not a complete linear system, you see. It's a part of this. It's not complete, of course. Right? Because here I took the complete linear system. But when you restrict a complete linear system, it is not complete anymore, because the map at edge 0 is not surjective. You have an obstruction. You have an H1 in the standard sequence, right? Okay? So that's the definition. It's a linear system of quadrics. Good? And now to finish things up, since I have the definition, let us look at some things. So I would like to estimate the dimension. So, problem? What about the dimension of this linear? First invariant, the dimension, right? What is this guy? Right? To do so, I look at the projection, and I call, W the image, right? This is non-degenerate here because I took a projection, right? And here I blowed up, and here I took E, and here I took the restriction. So this is my diagram, right? Okay? In general, this map is not subjective anymore. You don't know that, right? So you only know that the image is included in this guy. So you know what the dimension is at most C minus 1. So from this, obviously, it follows that the dimension is at most, the dimension of this guy is at most C minus 1. This is all we can say in general. One more thing. Exercise. Use. I give also the solution, but you should do the exercise. Use Terracini to prove that what is the dimension of the image here? The image of this map, not of this map. Huh? So this is, let me be precise. You know the answer? Maybe if you close your eyes, you immediately see the result. It's n minus delta. It's n minus delta. That is to say, the generic fiber of this map is of dimension delta. And this follows immediately from Terracini if you just think about it. Okay, perfect. So we know that. Now, what is then lemma 3 to finish everything up? So lemma 3 which it was observed by Russo and myself, but maybe it is a folklore type, but there is no, we included it in the paper because, so maybe it is folklore. The claim is if delta positive, and the proof is completely non-trivial, then equality holds. So it is the maximum possible for any dual second defective variety. And now indeed I finished the proof of the previous lesson, because now look, remember, here I proved it is conic connected, so it is defective, so lemma 3 applies, right? Right? So the dimension of this guy is C minus 1. But now remember, Lx was contained in the base locus of the projective fundamental form, right? Now be careful, here notation is projective. If you want vector notation, you'll have C independent quadrics, right? So Lx is contained by lemma 3 is contained in C independent quadrics. And this was what I used last time. Right? So it comes from this part. The proof here is kind of non-trivial. It uses some result by Zach and the Fulton-Lazarsfeld Fulton-Hansen connectivity theorem, and it's if I prove this, I'll need some more months. So please accept it. But I gave the tools and I explained practically how it works. Right? So Lx is contained in the base locus. This is of dimension C minus 1 projective. So this is contained in C independent quadrics. And then the argument proceeds as I showed, and you get the conclusion. Okay? I think it's not a bad idea to stop here, because then people will so I try to give a panorama of this thing, and I'm a bit in doubt for the last lecture because I have to choose.
On Monday?
On Monday, yeah.
Where we can find the details of the massivity, more details in the massivity?
Yes.
Where can you find?
Yes, you can, of course. So just look in our paper where it is explained. The paper is on archive, the last one. Ionescu Russo, manifolds covered by lines, dual defective manifolds, and the restricted Hartshorne conjecture. The last thing on archive.
Yeah, that might seem
It's preliminaries, the first proposition of the paper. And you'll see on what it depends and how the proof goes. It is kind of, I mean, I can explain it, but this will take, so I have to introduce several words, right? So I tried not to exaggerate, so I gave various arguments of distinct flavor, right? Something with playing with Chern classes, something playing with a dual and the second, something playing with manifolds covered by lengths and how you compute dimensions. So, right? This belongs to the universe of, let's say, Fulton-Hansen connectivity and applications to projective geometry. That's how the proof of Zach's theorems works. So if you know the proof of Zach's theorem from the Fulton-Hansen connectivity, it's the same film, the same movie. If you don't, this will be a completely new story, and people will will start being tired. So that's why I gave up to give this. So in the last lecture, I have to do some choices because obviously I won't be able to show you everything I wanted because 5 lectures would have been better. But I will I will make my choice such that it is a continuation of this, so you'll see some more hopefully interesting details. In particular, I will explain why the Hartshorne conjecture is true for quadratic, because this is really nice, and it will be. And I will quote the famous Falting's result, and then some other things. Here I have to think either to speak about dual defective, or to let this alone and to speak about the general philosophy of covered diamonds. So this will be my choice, because there is no space to do both. But I will try to. Are you familiar with Zach's theorems? Are they familiar with Zach's theorems? No. So maybe I should explain. I have a very sexy way of presenting this. It is jumping and diving theorem, and I will present it because it's hard to forget. It will be sexy. You have to come in beach suits, you know, because it is about jumping in the water and diving.
Okay.
And okay.
Thank you very much.